Okay, good afternoon, everyone. We've had two excellent sessions, both yesterday and this morning, and now we're beginning session number 3. The first couple sessions are focused on new avenues for collecting data on marine mammals, all these interesting data streams and technological advancements. The focus of this session will be slightly different in that we've got all this data from these different sensors. How do we integrate it and use it to go for our population assessments, kind of the holy grail of everything here. So we've got 4 speakers in this session. We'll have Rob Schick talking about abundance and distribution through data fusion. We'll have Caitlin Frazier here from Scripps talking about passive acoustic monitoring and integrating that into population assessment. We'll have Jeff Moore from the Southwest Fisheries Science Center talking about integrating multiple data streams to improve estimates of large whale entanglement mortality. And then finally, last but not least, Dr. Leslie New will be talking about taking these data and modeling population level consequences from multiple stressors. So we'll begin with Dr. Schick, Professor Schick, who will be joining us remotely.
All right. Hello, everyone. Everything look good on that end? Thumbs up from Andy. Okay, good.
Yes,
all right. Well, hi,
yes.
everyone. And thanks, Aaron, for the introduction. So the impetus for this work came from being part of the right whale community for a long time and sitting in a variety of meetings over the years where people have talked about, well, basically where are whales and where are right whales and how do we know where they are based on the different kinds of survey modalities. And people who had sort of focused on aerial surveys would say, well, we can fit models and this is sort of what the data looks like in terms of where we think whales are. And then folks who are focused on the acoustic side may say, well, okay, we have acoustic monitors in the water and it looks like the whales are here. And so there's some sort of frustration at the time to figure out ways to bring those two data streams together and sort of start thinking about, can we leverage the strengths of each one of them to come up with some sort of hopefully richer understanding of their distribution abundance. And so that was kind of the idea that sort of spawned a lot of this work, and it's been highly collaborative. And so I just want to acknowledge all my co-authors here that have contributed a ton of data and knowledge throughout the project. And I'll start by acknowledging the funding. The primary funder for the work has been the U.S. Office of Naval Research through 2 awards, one to SEA and one to Duke. But early on, I want to also acknowledge I got some funding from NOAA Fisheries and from CERTA that sort of helped kickstart some of these ideas too. So very grateful for that support. So here's kind of what I want to get across today. So some of you may be more or less or not at all familiar with the idea of what a spatial point process is. So I'll spend a little bit of a time in the introduction talking about sort of what are some of the ideas behind that. I'm not going to get too statistical, but just sort of give you an idea of the approach we're taking. We've done a lot of work in simulation, and in the interest of time, I won't focus on that, but maybe some of that can come up in the panel if we want to think about ways in which this could be applied to other areas. We've done a lot of work to sort of figuring out sort of optimal sort of ways to turn the dials and knobs to get better estimates, and so that's something that can be an important part of the toolkit. I'll spend most of my time talking about North Atlantic right whales in Cape Cod Bay. It's a small habitat, but one of critical importance to the species, and one that's been studied by Center for Coastal Studies and others for decades now. So I'll definitely spend some time talking about some of our key assumptions that we've sort of made and brought to bear to the modeling. So you can kind of assess it and see, what are the decisions we made and sort of how that contributes to the end results. And then finally, I'll end by sort of talking through some extensions that we're trying to build the model out with. Okay, so sort of the core idea here is we have these 2 different data sources. We have sightings that are from a plane, and then we have detections or upcalls that were reported from passive acoustic monitoring. And we wanted to figure out ways to relate those to a spatial point pattern. So a spatial point process is kind of the underlying thing. And you might think, well, okay, what does spatial point processes have to do with right whales or with whales in general? And actually, they've been in our community, as it turns out, for a long time. This is the earliest citation I could find for it. This is from a PhD dissertation in 1974. It was looking at spatial point processes in terms of searching for whales on whaling expeditions. So a slightly different application, but the same sort of idea in terms of the inferential framework, if you will. And for those of you who've done some distance sampling or density surface modeling, you're no doubt familiar with some of these more recent papers, certainly Sharon Headley and Steve Buckland's paper from 2004, which a lot of this work sort of, kind of built into the spatial domain itself is working with the spatial point process. So they're not something totally new, which is good. Now, for us, though, what was new was to consider out how the data that we have sort of relate to this underlying point pattern. And so here's one of the first big assumptions is that in this modeling framework, there's a true point pattern that I'm going to denote S. And these are the locations of the whales. And there's a true intensity surface that I'll denote lambda S. And we'll see a picture of that in kind of in the next slide. But it's really important because it's this intensity surface that once we sort of turn the inferential machinery and cranks, that we can integrate and get estimates of abundance, which is sort of what we want to talk about today. And so critical assumption, these are unobservable. So these are latent. We don't know what they are, but this is what we want to find out about. Each of the data sources that we do have provide a sort of partial realization of this point pattern, this true one. And there's a thinning mechanism associated with each one of those. And I'm not going to talk a lot about that because that's a detail, but it's an important detail I'd be happy to talk about offline. Okay, try to put a picture or a series of pictures to some of these ideas of what we might think about. And so this is just, again, simulation. So this is sort of early on in our modeling framework as we were developing the statistical model and framework. It's a good practice to sort of see if you can generate data from that model and fit it and to see whether or not your algorithms are working. And so this is this intensity surface that we're going to ultimately get to in terms of integrating out to get abundance. And so the idea here is that if you wanted to relate this to a point pattern of something like whales, you could draw a realization from this. And so in the areas in this image where it's sort of redder or warmer, you're going to expect to see more points of something. And conversely, when it's cooler, you'll expect to see fewer areas. So fewer whales or points. So if we draw that, one instance or one realization might look like this. So this corresponds to these simulated right whales. And it would be great if we could just simulate lots of numerous abundant right whales. It would be fantastic. Not quite there. So that's sort of the truth, if you will. And if you think back to my first assumption, when I mentioned that these are hidden, what we actually see is something that looks like this. And so this is, again, simulation, but this is, you can imagine a plane is flying back and forth over this area and following sort of distance sampling protocol, more likely to see whales that are available to be detected and closer to the transect line. And that's what's sort of shown in this red. So here's the first glimpse of the way to see like what's the truth and then what's actually observed. So that's one. And conversely, you might imagine if you had a passive acoustic monitoring array in the area, you might expect to see or hear, excuse me, whales that are calling in these kind of warmer, hotter areas, if you think back to that intensity surface. And so these are simulated calls detected on these hydrophones. Okay, so that's simulation. And so let's look at a little bit of real data before we sort of dig into a couple sort of nitty-gritty details of the modeling framework. So we get to build on work that Center for Coastal Studies has done for not just years, but decades. So big shout out to them. And so the data here on the left-hand side correspond to two different data sources. So I'll just animate and walk through them. So this is the location of the hydrophone array that was put in place by Chris Clark when he was at Cornell. And the size of each of these red circles around each of these 10 hydrophone arrays corresponds to the number of upcalls that were detected on each individual array. And critically, and this relates to one of our assumptions, these are the number of upcalls recorded during the time the plane was up in the air. So there's a time overlap between those two. These are these canonical flight lines that CCS flies and have done so for a number of years. And so this is what was flown on the day. And then these are the whales that were seen from the plane. So a couple things to think about. You can sort of see at the bottom hand that the plane was only to make it about halfway through the bay, I think because of weather on this particular day. And so if you wanted to do a traditional distance sampling analysis, you're going to be limited to the lower half of the bay. And pedantically, you'll probably really have a hard time doing it because you only saw 5 whales on this day. And so if you think back to sort of the Buckland et al. References, there's just not a lot of whales to do a distance sampling analysis on. However, clearly whales were in the northern half of the bay because we heard lots of them calling it as denoted by the data. So the next day, the weather was better, more cooperative, and they were able to fly the whole suite of lines throughout the bay. and saw more whales, as denoted with the blue crosses, and heard some whales on the array, but the calls were many fewer. So unlike in simulation where we know what the truth is, here we don't know the truth is. So the challenge is to take these data and get back to the underlying truth. So I'm just going to talk through some of the assumptions because I think they're important to think about in the context of trying to use this approach for other areas. So we have this underlying spatial process that I've talked about. It's fixed in time. So we're treating the time window as snapshots, and that's an important assumption. We're lucky that in addition to having a lot of data being collected in this area, a lot of data has been analyzed in this area. So there are detection functions that are known. That's thinking back to that sort of thinning process I mentioned early on, both for the aerial data and also for the passive acoustic data. So they're parameterized and we're using parameters, but we're not estimating the sort of shape of those, if you will. So that's one assumption that's also important to think about. So we want to know about availability and we want to know about call rate as we sort of put this model together. And we're lucky that Susan Parks and Dave Wiley had done a series of DTAG deployments in Cape Cod Bay. So we were able to make use of that, as I'll get onto in a couple of slides. So they're really helpful and they're important to sort of getting at estimates of abundance. So they're available and we use them. If you don't have them, you could fix them. Or you could assign some prior. So that's another assumption to think about. But we did have them, so we were going to use them. And I know Andy loves it when I share slides full of equations. So we'll just have one of two here, but just to kind of give you an idea of what the full likelihood for the model is. I know at least some people will appreciate seeing this. So this sort of S sub L is the locations of the whales that are seen from the plane. This N sub K are where the calls were detected, and the K corresponds to the index for each one of the 10 hydrophones that are in the bay. And then the Z's are the surfacing data from the DTAG, and then also the Y's are the call data from the DTAGs. So we want to learn about this pi parameter in the middle, and we also want to learn about the C. So pi is our availability, so how likely is the whale to be close to the surface to be seen from the plane, and then C, what is the call rate for individuals. So as is probably not a surprise to anyone, the results are sensitive to that call rate. So that's an important parameter to think about. And because of that, I'll just dig into it a little bit more in this slide. So this is sort of what we want to make inference on. We decided early on that this sort of, this spatial surface is important for us. That's kind of the key object of our inference, because again, we can integrate that and get to our abundance. So that's the data. So those are known well. And from a modeling standpoint, fitting a Poisson model to those is pretty straightforward. So we want to learn the sort of hydrophone specific mean of that Poisson, and that's pretty straightforward to do. As I mentioned, we have detection functions. So this is from a paper that Caitlin Palmer published in JASA in 2022, just a couple of years ago, on data from Cape Cod Bay. So we're able to use that, which is nice. And then there's the C parameter that I mentioned. So you can see here in this sort of middle equation, there are kind of four components to that. And we decided we wanted to learn this lambda sub S, as I mentioned. And so you need some information for these other components. Otherwise, the whole thing is just going to be hard to fit and make inference on. And I'll asterisk that C parameter because as everyone would expect, that ideally we'd want sort of a spatially and temporally varying call rate, not to mention having it sort of life history specific and individual specific and whatnot. The data just don't support that parameterization, but that's something that we would like to do if possible. Okay, so a couple of slides to walk through the results before I move on to the extension. So this is that lambda sub S. And so for these two days, two consecutive days that we use, this is what we get. And so a thing that's important to think about, we want to know abundance, of course, but this allows us to look at global abundance. So we can integrate all of this and just say, okay, on these 2 days, these are the number of whales are in there. But it also allows you to do local inference because there's sort of a spatial model behind this. So I'm not showing it on here, but it is in the paper. If you wanted to look at specific sub areas in Cape Cod Bay or in any other region where you might apply this to, you can also get estimates of abundance with uncertainty. So that's an important feature to just point out. When I was talking through the data on the left-hand side, I said you wouldn't be able to do this on the northern half with a traditional analysis of the northern half of the bay. And so what we're showing here is we're all able to do this and produce estimates of abundance, produce this intensity surface. And you'll notice that if you think back to when I showed the data, there were no flight lines up there. So there was no sort of precise spatial locations of the animals. And so that intensity surface is kind of softer or more diffuse in that area. Conversely, when you look over to April 10th, where the likelihood sort of was dominated by these aerial survey data. And so the intensity surface is sort of more finely resolved in and around the areas of those sightings. Thinking through sort of serious injury and mortality, unfortunately, that's something we have to deal with a lot in the right whale community. And so if you wanted to say, well, okay, how do these estimates impact our sort of understanding of possible anthropogenic impacts or effects in this area? You can imagine a boat, in this case, a cartoon boat, coming out of Cape Cod Canal, transiting through the bay, and then heading up into the Gulf of Maine. Well, from just a ship strike standpoint, you can look at that sort of local spatial interaction in a really sort of nicely refined way, also incorporating that uncertainty that I mentioned about. And so this is led by my colleague, Aaron Schleep. This was published in the stats literature late last year. Okay, and so thinking through of some extensions and some other areas where we might apply this, this is a paper that we actually just published last month, also in the stats literature. But the idea here was to sort of take that framework that Aaron and all of us developed together that was using, if we look at the top panel here of this graphic, using the hydrophone locations and the calls on the hydrophones and also the aerial survey data shown with the blue crosses, but then adding in information on zooplankton. So CCS also collects an amazing amount of information on the zooplankton resource, the prey of right whales in this area. And so what we wanted to do then, since we're thinking spatially, was to build a spatial model for the prey that's shown in the middle panel here. And that builds off a paper we published as part of the CERTA project a couple of years ago, and then estimates this abundance. So we get abundance like we did in the previous slide, but we're also making this a little bit more biologically rich because we're getting sort of a predator-prey interaction here by being able to estimate these coefficients across the zooplankton and the whales, and show also that we're able to sort of more finely resolve the estimates, both of the zooplankton and of the right whale distribution we model together jointly. Okay, getting back to my assumptions. So we fit a spatial process, and you might logically think, well, a spatial temporal point process might be more natural and more sort of interesting and a good fit for these data. And you're right, if you're thinking that. It's hard because in this case, the continuous data that we have to be able to sort of look at a continuous process evolving over time are the PAM data. The aerial survey, despite the fact that I showed you two back-to-back aerial survey data, they're usually flown every 2 weeks throughout the season. So we have these snapshots from the air. And to be able to do that, you need more information on linking the calls to the individuals, which we don't have. We do have some data on this that have just localized calls, and we're working on fitting a model to that, but not linking to abundance. This would just produce an intensity surface of calls. So that's something that's interesting biologically, but perhaps not necessarily in terms of the abundance. So without some kind of underlying movement model or ability to link calls to specific individuals, and ideally a behaviorally sort of indexed rate, like I mentioned a few slides back, that link is going to be hard. So where am I going to be able to apply this? Well, anywhere with these similar data structures. So line transect data and PAM data. As I mentioned, we had the information, the ancillary data information, and that was informative. So those are good to have. But if you don't have them, you just have the top two, you could use them. And three possible places I've had some initial conversations with colleagues are Southern New England, Monterey Bay, and Gulf of Maine to apply the model that I've just talked to you about. People had some QR codes earlier this morning, and I didn't think to put those in, but I'm happy to sort of send anyone a PDF or talk further about the papers that I've mentioned after the fact. And with that, I'll be happy to take any questions or save them for the panel.
Thank you very much, Rob. We have a few minutes for questions. So per previous patterns, if we have commissioner or scientific committee questions. Go ahead, Andy.
Andy.
Hey, nice job, Rob. Really interesting. I'm slightly afraid to ask this question, but because we're thinking about things in a stock assessment context, can you say something a little bit about how uncertainty propagates through? Because if we were to use that abundance estimate generated like this, that uncertainty will eventually propagate through into like NMN, which propagates into PBR. But How does that work in terms of there's multiple data streams, all of which have their own sets of uncertainty?
Yeah, that's a great question. So I won't say it's all fully accounted for. We tried to fully account for it all in terms of like, every bit is sort of, well, not every bit is parameterized, but most things are parameterized. I think the thing that we found was the most certain to, or most sensitive to, excuse me, was the information on the call rate. And so, which is, that kind of makes sense, right? But since we're looking call rates on a hydrophone as opposed to a localized call. So that was a big one. And so I think anything that could help inform on that better is going to be critically important. The other places where there's uncertainty, and we were able to sort of not fixed ones, they are parameterized, is the detection functions. So with the PAM, the hydrophones, of course, record ambient. So we have ambient in that detection function, but we weren't estimating that detection function. So it's possible if you're thinking about like, well, if you don't have that acoustic detection function in Southern New England or Bay of Fundy or wherever else a similar data set might have, then that's going to be a place where there might be some uncertainty that needs to be accounted for better. But it's a good question, and there are a lot of pieces of it.
Awesome, thank you.
Any other questions? I have a quick question. Oh, go ahead, Erin.
Hey, Rob, thanks, that's great. Adding on to Andy's question, did you make spatial maps of uncertainty to see variability and uncertainty between grid cells? And then does effort across the two different platforms, your visual surveys and your acoustics, impact that uncertainty spatially?
That is a great question. I'm going to reshare if I can back to my PowerPoint. The answer is I don't have them in front of me, but I do have this. So I'm going to give you a partial answer to that. So this is what the sort of the detection surfaces look like mapped out spatially. And then if we go back to the intensity surface, I showed you that value. I just showed you the posterior median, but I can integrate over that and sort of map out that uncertainty. I don't have them at hand, but they are available to be produced. So one take home for us when looking at this is, because the aerial survey data our lines are spaced so closely together, the detection, as you can see in the top right corner here, is pretty high as we're able to fly across the whole bay. So partially yes to your question. We have them, but I don't have them at hand to show you.
Cool, thanks.
Great, thank you, Rob. I think we'll defer the questions until our panel discussion. So we'll move on to our next speaker here. Our next speaker will be Kate Frazier. She will be talking about advancing acoustics for integrated population assessment. She has worked on passive acoustic monitoring for many years and is in charge of the LISTEN project in the Gulf of Mexico. And she's got her fingers in a bunch of pies, but I have to say that when I think of her, I think a lot of applying a lot of data mining, machine learning techniques to very large data sets. So it'll be interesting to hear what she says. Kate?
Hi, everyone. Thank you for the opportunity to speak with you today. Really looking forward to discussing this project with you. So I'm going to talk about advancing acoustics for integrated population assessment, and Rob focused on a baleen whale example. My example is going to focus on odontocetes. And this project is a long-running collaboration with the Southeast Fisheries Science Center, Melissa Soldevilla and Lance Garrison out there. So this story starts 15 years ago. If you cast your minds back to the Deepwater Horizon disaster in 2010, John here from Scripps had got some underwater acoustic recording packages ready and deployed very quickly after the beginning of that event. I think it's fair to say that this was pretty early in our efforts to quantify marine mammal occurrence with passive acoustics, but we put these sensors out, picked some sites as close to the wellhead as we could get. That's the Mississippi Canyon MC site on here. You can see the surface oil expression, maximum extent in the brown. We picked a couple of other deep sites to the east and west for comparison, and then some sites on the shelf. So a main pass site at about 90 meters and one over in the Rice's whale habitat near DeSoto Canyon. And with a lot of help from our friends, we kept these things going for the next decade, accumulating data, and you can see our ultimate recording effort over the following 10 years in this plot on the bottom here, which I think is pretty good for putting electronics in the ocean, right? So while those were soaking and accumulating vast amounts of data, we worked on a number of things required to get from the acoustic recordings to something that means something to someone who's trying to manage marine mammal species. And so 3 main things were involved in that. And the first one is getting to density, right? So we think it's critically important to be able to speak the same language, compare apples to apples between these methods, and getting to a number of animals per unit area is that key for us. So what we have implemented following the methods of Tiago Marx et al. In 2009 and subsequent innovations there related to that is a point transect monitoring approach that's basically the corollary to visual survey methods, right? So for each thing that you have to do in a visual survey to get to an estimate of density or an abundance, we do something similar in acoustics. So we have a probability of detection, right? On a boat, how likely was it I was going to see this thing? In acoustics, how likely was it that I was going to hear it? We have vocalization probabilities that we incorporate from the literature, and those are the equivalent of, was the animal available to be seen when you're in a boat context? Was it vocalizing in an acoustics context? We use group sizes, species-specific, for our density estimates, and we incorporate detection and classification error rates from our automated processes that we use to find these millions to billions of echolocation clicks that we use for density estimation. We review a subset of that manually and come up with those error rates. So that getting to density was one key innovation in that period. The next one was acoustic tracking. So acoustic tracking is really intuitive, right? It's just the same way your 2 ears allow you to hear whether something's approaching and locate it relative to yourself. We use multiple hydrophones and compare the time differences of arrival of the signals across those phones. And so by building on that strategy, we've been able to do 2 key things. One is understand subsurface behavior of deep divers, deep diving odontocetes. And that is really critical for helping us figure out that likelihood that we are going to hear something, right? We need that behavioral insight. The second is to validate our models, right? So that we can ask, well, I think I could detect something out to this distance, and can I actually do that? We can validate that with this tracking information. So we've done a lot of work on this. I love this video from a student in our lab where you're seeing 7 different goose-beaked whales diving simultaneously above an array. So this is a really powerful technology. The third piece has been trend analysis, right? For Deepwater Horizon, we really want to know about long-term impacts. And so we put a lot of thought into coming up with robust methods for trend analysis. And the way we currently do this is we take our raw time series. In this case, we're looking at daily density estimates at one location for Rizzo's dolphin. We find a seasonal adjustment, a seasonal component. That inset there is our seasonal adjustment for this species. Not all species in the Gulf have a seasonal component, but this is a nice example. we deseason the data, and then we fit a trend line to the deseasoned data. And then at the bottom, I'm showing you that trend line over the original data, offset by the total median density. Then the method that we've selected for trend analysis, the FIT method, is a Thielsen regression approach. And we selected this because it's a very conservative trend estimate that is not heavily influenced by outliers. You can see an example comparison with how least squares methods respond to outliers. The way Thielsen works is you basically take a slope between every possible pair of points, and then you compute the average of that slope. So it's very robust. We like robust estimates because we don't want to overestimate change in our time series. And it doesn't have any assumptions about data normality, which is convenient because our data are not normal. Rare species trend estimation, I just want to flag this as this is hard. It's hard with any regression type of fit. And this is no exception. So for rare species, always difficult to know whether change is truly happening. So after 10 years, now we're circling back with these methods in hand to our long-term trends in the northeastern Gulf following Deepwater Horizon. So this was published late last year. We see long-term declines that have exceeded and outlasted the expected declines in this area, based on the damage assessment models that were produced. And if we look at this in a table form, here are our 3 main deep diving species in the Gulf, showing you the mean estimated densities in 2010 and 2020 respectively, and the percent change over that decade in between. And I've categorized these as decreasing, increasing, or neutral. Decreasing means both confidence intervals entirely fell in the negative. Increasing, both entirely fell in the positive, and neutral would be spanning 0. So we're seeing declines for these deep divers at some of these sites where they were surprisingly dense. Dry Tortugas, I don't think we'd ever seen densities of goose-beaked whale as high as we saw there shortly after the spill. And these declines are on the order of 70 to 80% maximum, and even 30% for sperm whales is a lot. Similarly, for the smaller delphinids, here I'm showing 4 different groups. We grouped some things together. So we have Rizzo's dolphin, teased apart. We have a category of oceanic dolphins. These are mostly the Stenella species, spinner dolphin, pantropical. In these 3 panels in the middle, we have a group of shelf dolphins, that's bottlenose and Atlantic spotted in the Gulf, and then a catch-all for these large, I'll call them blackfish, right? Killer whales, pilot whales, things that make low-frequency clicks. And for many of these, we also see long-term declines. It's a little bit more of a mixed story, but definitely for these small oceanic dolphins in deep water, we saw declines between 15 and 30%. Rizzo's dolphins also considerable declines in deep water. And the one outlier is this category of blackfish, where densities are very low to start and still low at the end of our monitoring period, but slightly increasing. But that does not make up for the fact that we're getting hundreds of animals fewer per 1,000 square kilometers for other species. So at the end of this project, we had a lot of data, we had a lot of interesting trends, but we really didn't know how this related to the whole Gulf, right? We're just looking at this one corner. And so we expanded this effort Gulf-wide. And so we have our historic sites, and we have added additional sites. We had a vision for how we would do this with stationary sites and sites that move. So the stationary sites are these red crosses. We've come up with, Len Thomas helped us come up with a scheme where we basically have repulsion zones around those, and then we place a random set of sites that move every year on this colorful map on the bottom corner here. And so the idea there is that we go out once a year, we replace the instruments at the black crosses, and we move instruments between the years 1 and year 2 and year 3 sites, so we're covering the space. It's a huge effort. And to give you an idea of the data, so from the long-term sites, we'll get this a little outdated, but here's an example of 3 years of continuous data at the long-term sites, and then little kind of annual snapshots at the short moving sites. So to horribly generalize this petabyte of data that we've collected at this point, you can kind of zoom out, and here I'm representing the mean density of each species as the area of a circle for our 6 main categories here. What's amazing about this is we're starting to get this unprecedented view of species, kind of the general patterns of species distribution across this giant area. And it makes sense, which is very gratifying, right? These patterns are not random. We're seeing, for instance, for sperm whales, we have high density up in the Mississippi Canyon area. That was our highest site originally, and still we haven't found any sites that have the level of sperm whale occupancy that one does in all of our other sites. Goose-beaked whale, we've found at these really steep topographies where currents are strong. And we found this unusually high site off of the Campeche Escarpment, which seems to have the same densities as we used to have at our old Dry Tortugas site, which now is 80% lower than it was 15 years ago. Gervais-beaked whale, in contrast, is in deep water, pretty disconnected from the slope features, mainly in the loop current affected waters also, which are kind of this strong current that comes up from the Caribbean and then eventually turns into the Gulf Stream. The oceanic dolphins are also very strongly linked with that feature, and we see more of the blackfish and Blainville's beaked whale down in the southern Gulf. Okay, so now what we are doing is comparing that with oceanographic features, because we want to actually officially quantify that, understand these relationships. And so my colleague Alba Sosana Berga here has been working on developing descriptors of those major oceanographic features and trying to understand why we see these species where we do. And one really nice piece of work she's done is look at the surface waters in the Gulf and the movement of those in this top panel, and how different that is from the deep Gulf circulation, which is down where our beaked whales are foraging, right? So we're trying to understand those dynamics and not just limit ourselves to the obvious, chlorophyll and sea surface temperature and whatever you can measure at the surface. It's really getting into what are the dynamics down where it matters for our animals that are searching for prey. And I really like this visual, which gives you more of a sense of the power of the data. This is daily resolution densities. The blue dots are our different sites, and you can see how the densities rise and fall as this loop current feature moves and pinches off eddies that then move through the Gulf. And so it's a really dynamic system, and there's clearly these relationships between where animals are choosing to hang out and how that oceanography is evolving. So we are currently working on understanding this with the use of basically souped up random forest trees. But this is a really nice example from Alba of her work on trying to distinguish at these different sites, what are the dynamics. And what we've learned so far is that different things matter at different sites. So the same predictors don't have the same level of influence at all locations. And in this case, she's comparing a site on the Campeche Escarpment to one up on the Texas and Louisiana shelf at Green Canyon. And she's got the 5 most important predictors in the top corner here at each site listed. And what's really interesting is that some of the variables are the same. How much of this surface water is there versus this deeper water? Those are the thicknesses. But in the northern Gulf, actually airgun noise pops out as a really important predictor in those oil fields, right, where there's lots of seismic surveys. And in the southern Gulf, that is not an important predictor. Rather, the currents along the slope there seem to be more important. And she's done a really nice job of digging into that black box and understanding which factors are influencing what and when. So this is a work in progress that we'll have out soon. Okay, so just to pause here, the takeaways from what we've done so far are that we saw density declines for 7 of 8 marine mammal species or species groups in our long-term study from 2010 to 2020. Marine mammals are clearly not uniformly distributed across the Gulf, right? We have these hot spots that are really defined for and consistent year to year between species. We see patterns in occurrence that are complex and seem to be driven by oceanography, but we know that there's sort of a mediating factor of prey in the middle that we don't know a lot about, right? And that these drivers differ regionally. We also see this interesting partitioning, right, in space and probably also in depth of these different species across the region. So there's not one pattern that fits everybody. Okay, so where we're going and kind of why this matters for what we're talking about here today, we really want to combine this data with the acoustic data, or with the visual survey data, and we're in the process of starting up a renewed project to work on that with Southeast Fisheries. So we have done this before. We did a pilot study that published back in 2021 where we took visual survey data from the Gulf and our acoustic data from the historic sites and looked at, okay, if I train a model just from the acoustics, how well do I predict the visual sightings, and vice versa. Okay, and what if I put them together? How well does my model predict the other data type? And this was a really useful exercise. You can see us wrestle in that paper with kind of what Rob was talking about, where you have an underlying truth and you have two different observations of that truth that you're trying to reconcile. And so I think this has a lot of promise for reducing uncertainty in cryptic species abundance estimates. We have the benefit of the year-round measurements in the acoustic data that are really complementary to the visual surveys. We can look at spatial shifts, and we also have this high resolution that's useful for understanding the oceanographic drivers. Needs. So there are still holes and things that we need to improve on. Number one, I would, wave a flag for oceanic dolphins, right? That we need more effort applied to distinguishing those species the way there's been effort on the beaked whales. And I think it's totally possible. It just needs more dedication. Tracking for more species to understand subsurface behaviors for more species is needed. And then this missing link of prey is really critical. And I wanted to highlight some work that Simone Bauman-Pickering here at Scripps and her student Shannon Dolan have been doing, bringing active acoustics to bear on this question. So co-deploying passive acoustics with the active and the tracking hardware so that we can look at where beaked whales in this case are foraging in the water column and how that relates to different targets, right? Small targets at depth, large targets at depth, small targets higher up in the water column, and that is all changing with these oceanographic drivers out here in Southern California. And we just started a copycat study in the Gulf to mimic this setup. Okay, so closing the loop, we implemented this crazy random number generator driven design in the Gulf so that other people don't have to, right? And it takes many, thousands of miles traveled every year to go do this and reorganize our sites and move stuff around. We've collected at this point 5 years of data. We're about to do 5 more. We're in a position where we can start to ask questions and validate the existing species distribution models from visual survey effort in the past. But really what we want to know is kind of what's the long term here, right? Like what is the minimum number of sensors? What's some reduced size of this project that could get us the answers we need sustainably for the long term? And I think unfortunately the answer is it depends, right? It's going to depend on our species priorities and how much confidence we need to have in our answers, our sensitivity requirements. But I think 2 things that we've learned so far is that these short-term sites have been very helpful for characterizing actual spatial distributions across the region. An amazing sanity check for trying to understand the big picture. But the long-term sites are important for detecting change, right? So a mix of the two, and a mix of the two may be needed ultimately to produce and keep producing good abundance estimates over the long haul for this region. Okay, and that's all I had. I do want to thank the other project partners and recognize their contributions. We have two partners in Mexico, Adolfo Gracia and Arturo Serrano, who are key to this project. We have Mathieu Lehenoff, who is our resident oceanographer, and Carrie Walbell is our long-suffering data manager. And many, many people made this possible, and many, many funders have supported us over the years, including people in this room who have lended a hand when we were in need. So thank you, everyone. Happy to take any questions.
Thank you very much, Kate. Unfortunately, to stay in time, we'll just have to move right to the next speaker, and please keep your questions for the panel discussion. So our next speaker will be Jeff Moore. Let me see if I can get back here. Brady, I'm going to trust you to get the next presentation up. So Jeff works at the Southwest Fisheries Science Center. He is the lead scientist for the California Current Marine Mammal Assessment, with expertise in marine mammal demography, population dynamics, and fisheries impacts. Excellent. All yours.
All right, thanks everybody, and thank you to the commission for inviting me to come speak today. I appreciate it. Okay, so I'm gonna, oh, let's see, that's not showing up top right now.
No, I didn't. Give me a second, sorry. Show the right screen. I'm curious. I think it's possible. Let me stop the share. And reshare. Oh wait, we need presenter. Slide. MA2 presenter view. No, it's not you.
That's true.
Yay.
Thank you.
Yeah, but I'm not sharing the screen, unfortunately. And let me just, before I leave, let me just make sure. Robin, would you check my screen? Is it sharing it on there? Apologies, everyone. Let's try this one more time. So this should be here. And then we need to. Felt like we had a good system earlier.
You do.
I think we're here now. Thanks, everyone.
Okay, great. Okay, so I'm going to be talking about kind of a long-standing challenge that we have on both of our coasts in U.S. fisheries management and other countries where for certain types of species that get caught in fishing gear, it's kind of hard to know how much of that is happening, right? We know it happens, we have reports of it happening, but for various reasons, we can't put an observer program into this particular context, and so it's difficult to extrapolate what we know to what we don't know. And that is, let's see, can I arrow? Click on what, sorry? Okay. I should be able to just arrow, right? Did that work? No. It's working on here, but they're not advancing up there. So can I go in?
Oh, it's because we're not PowerPoint anymore.
Okay.
So we just go down here. And, oh, interesting. It's still not not in presenter view. From beginning. Yeah, it's just interesting that we're not in presenter view, which it has been.
Can I just click on that?
Just move this around down here. Let's see. Reopen it. We just close PowerPoint and start all over.
Okay.
And we do have, I think, 5 extra minutes of extra time, so you're not losing anything. So it is currently, no.
Go to that slideshow setup.
Let me just see. Oh, let me just go in here and click display settings.
Yeah. Okay. You want to just share this screen? I mean, display the screen up there?
I want him to be able to see his own note slide.
I don't have any notes.
Oh, you don't?
No.
So then we can just temporarily share this one. Temporarily
Well,
we'll
no,
share.
we need to put it up there too, though.
Like I can just see it
That's a
down there,
different
that's fine.
Just share that.
You can drag it over.
Let's just reopen this thing again. It's number 3?
There we go. And then,
There we go.
okay, we'll just
Yeah,
hide
but
this.
how do I hide that? Just click.
That. And then hide floating meeting control.
Oh, there it is.
And you'll have to click back on this
Click
too.
it in there. Oh, no, now it should
And now
go.
you should be able to use the.
There we go.
Let's thank our speaker for a great presentation.
You're funny. Okay, so this is about humpbacks on the U.S. West Coast getting entangled in fixed fishing gear, mostly from crab fisheries. This is just a trend over time of the number of entanglements that have been reported, and you can see they've gone up, particularly over the last decade or so, with the blue part of the bars being humpback whales, so mostly humpbacks, and that's what I'm talking about. Okay, like I said, it's difficult to get at the true MSI is mortality, serious injury. Difficult to get at true MSI from what we observe because these are not observed fisheries. Animals swim through the gear, they carry them off. So we have opportunistic reports, and those have traditionally been what have gone in our NOAA stock assessment reports. So we know essentially a minimum value of how many animals are getting entangled and injured, but we don't know the true number. And this is a management issue. The numbers in this table are a little out of date, but we have a few different humpback whale stocks that inhabit the U.S. West Coast during summer in particular, a couple of which we're most concerned about because that's what we mostly have here, and they're listed in the Endangered Species Act, endangered in the case of the Central American stock, threatened in the case of the animals that come from mainland Mexico. And these are semi-recent PBR values for those stocks compared to observed MSI. And you can see that for the Central America stock, it's already exceeded. And for the Mexico stock, it's not exceeded, but it's similar order of magnitude. And just so it kind of begs the question of whether it might be exceeded in reality, if we could estimate it. So that's what I've been thinking about is can we obtain an accurate estimate of actual mortality and serious injury for these guys? And so I guess, you know, the title of this session that we're in right now is Innovative Quantitative Methods, ... There's not really anything innovative quantitatively in this work I'm doing, but I think, you know, maybe the innovation is a little bit in some of the insights that I've tried to bring to thinking about how we can use information that we do have about these stocks to get at some inference on this question. So here's a little bit of maybe Andy-friendly math, and hello, Andy, nice to see you. So general conceptual framework is that our total entanglements might be estimated as the number that we see divided by some detection rate, and that detection rate is what we're trying to get at, that we've not been able to kind of tackle before. So a couple approaches came to mind. One was that, so some of you might be familiar, I'm sure many of you are familiar with the Happy Whale catalog that exists for humpback whales in the North Pacific, where essentially it's a data repository of photo ID information contributed by whale watchers, researchers, and there's just heaps and heaps and heaps of photo ID data. And so we know for whales in general, humpback whales in general, what fraction of the estimated population size we see in any given year. And so one question we kind of brought to the table is, well, if we assume that the sighting process for entangled animals is not that much different than the sighting process for regular animals, then maybe whatever we glean from Happy Whale, can we just apply that to entangled animals and get it a detection rate estimate that way. And I'm not going to talk more about that approach in this talk, just in the interest of time. It's not the preferred of the couple of approaches that I've been pursuing, although you actually get fairly similar answers from that. So, but I'm going to talk more about the second approach. So again, we get reports of entangled animals up and down the U.S. West Coast, and I called up our regional office folks, and I said, do you get reports of animals again, of the same animal, like weeks or months later than the first time you saw that animal? And they said, yes, that does happen from time to time. And so I started exploring the notion of treating sightings and repeat sightings, resightings of entangled individuals as encounter histories that we might be able to apply simple survival mark recapture kind of methods to, where the first time an animal is seen, kind of treat that as like an initial capture and marking event, and then you look at a time series of that same individual being reported again and again and again, and then not again, and then essentially we have some kind of probably biased version of a Carmack-Jolly-Sieber kind of framework. So that's kind of what I pursued. That previous slide was just a quick scan of the data. I'm going to skip past that in the interest of time. So this is what like an encounter history might look like for a handful of individuals, where the ones are the first time we saw the animal, and then every digit later is a week later, and we did or we didn't see it. And this is actually 6 individuals, real individuals. So we do see and re-see the same individuals from time to time. For the most part, we don't, but for a fairly substantial number, we do. And so I went ahead and tried to apply some Carmack-Jolly-Sieber methods to this. So just a real brief summary of the data. So over the course of the last 11 years, we had 257 reported individuals as being entangled in these gears. A number of those are, okay, so there's a couple of sets of boxes going down. The ones on the left are data from 2014 to 2024, and the ones on the far right are if I just look at the most recent 5 years of data. So you apply some filters to get rid of some things that don't make sense to include in the data for one reason or another. And what I ended up being left with was 175 cases for trying to estimate detection rates. But then just using, let's say, the 60 cases on the far right as like the count value for coming up with estimates for the most recent 5 years. So, yeah, if I were using the full 11-year data set, you could see I have, the 231 would be informing that numerator, the 175 would be informing the parameters of the detection rates. So for those familiar with Cormack-Jolly-Sieber methods, you know there's two conventional core parameters that you're estimating. One is the phi parameter, which is conventionally referred to as like an apparent survival parameter. I'm referring to that, I'm just calling that something different today because of how I'm interpreting it. And it's the probability that through time an animal is still available in the system to possibly be detected. That's to say it's still in the study area, still alive, and still has gear on it. And then this conditional detection probability. So given that the animal is available, what's the probability that you actually see it in a given week? And then you could just do some algebra, and from those parameters you can come up with this parameter of interest, which is what's the marginal probability that if an animal was ever in the study area with gear on it, you would have seen it at least one time. These results are really preliminary right now. I'm still very much working with the data, and the numbers change a little bit week to week as I tweak some things in the code and you know, change some data filters and stuff like that. But it's all I'm very much in the ballpark right now, I think. So out of like the 175 cases that were used to get at the detection rate parameters, there were 18 individuals that were seen more than once. So it's not a lot, right? And it tells you instantly that the likelihood that you're missing a lot, right? Like out of, you know, only 10% of individuals were seen in more than 1 week. So you know you're missing a lot of stuff out there. And animals tended to not be seen more than about 4 months later than the first time they were originally reported. Okay, top values, no boxes around them. Those are those core model parameters that by themselves don't have a whole lot of interpretation in this particular context. But when you do the algebra, I'm estimating that I think there's probably about a 1 in 5 chance that an entangled animal ever gets sighted. And so you apply that then to the counts of actual animals you've seen, and so you get some estimates. So here I have an estimate of entanglements for the last 5 years, about 430 animals over the last 5 years, or about 86 per year. Did some goodness of fit testing. Not going to spend any time on that. Just I took a simulation approach where I generate encounter rate data from the model parameters I estimate, and I look to see, you know, if you do that like thousands and thousands of times, do the simulated data sets look like the real data? And if they do, then that gives you some assurance that the model that I'm applying to the data could have been the data generating model. And they fit reasonably well. They don't fit, the goodness of fit's not perfect. There is definitely some sign of individual heterogeneity in there. I have another data set as well that I don't have time to talk about that definitely shows indications of heterogeneity, individual heterogeneity. But the fit's really not bad at all, especially for a simple model. And so I'm fairly satisfied at the moment to keep moving forward. The assumptions are important, very important. Top assumption applies to the denominator, the detection rate. And it basically says the animals in my sample are like the animals that aren't in my sample. And this is a textbook case for something known as survivorship bias, which is that the animals I have are the ones that lived and got to be seen, right? And so they're probably more detectable than the ones that you never saw. And so if anything, we're probably underestimating true entanglement right now, but still I think we're definitely like a lot closer than we used to be. And then the bottom assumption is referring to the quality of the numerator, right? So we have, the numerator is just the count. How many individuals, how many entangled cases do I have? And I'm assuming that there's not error in like, I get an entanglement case today, and I feel confident that that's a different animal than one reported 2 months ago. And I've worked with the West Coast region a bit. They've developed a protocol to quantify what they're calling the uniqueness of reports and uniqueness of cases, and they feel very highly confident that the vast majority of cases are in fact unique. It's not perfect, and I have an adjustment for that in the math here. Okay, so from entanglements, we have to go to mortality and serious injury. That's a separate process that NOAA does to identify cases as seriously injured or non-seriously injured. It's about 80% of these animals are considered to be serious injury cases. So the arrows just shift your entanglement estimates to approximate MSI estimates right now. And I've yellow highlighted the annual value and compared that estimate to the just reports that are in the sum yellow highlight down below. For those are actually slightly different time periods, but so they're not apples to apples, but they're close. So as you can see, the estimate is several times higher than the observed values. Okay, so what is that? So now that has to be apportioned to the different stocks. There's yet another different process for doing that. So how's that going to play out? Well, Central America, again, we're already exceeding Central America PBR just on observations alone. For the Mexico stock, it's going to be like kind of in the same ballpark as like our estimate is going to be kind of in the same ballpark as PBR for that stock. I think, yeah, that's the punchline. Lots of people have helped with this. West Coast region folks have been very kind in helping me interpret and look, providing me the data sets, helping me interpret a lot of stuff. I've been working a lot with John Kalmakidis, particularly on that first approach that I didn't really talk about much in this talk. My Southwest Center colleagues, including Karen here, who've been sounding boards for this work, and then I've had a number of other reviewers of this work so far who are listed down below. So let's see, one thing I would like to mention is, so implications for this is that, apart from the management context at hand, I've already had folks in NOAA who are involved in running the stranding programs kind of like asking for suggestions on if they should be collecting some of their stranding data a little more differently. Because, maybe they're not keeping track of whether the same individuals are being reported, in different populations on different coasts. So I do think that yes, they could do something a little more different. Anyway, I'll end it there. I know I got started behind anyway, so. Okay, great.
Yeah, I'm going to get the next one set up. See if we get this.
Thank you, Jeff, and I apologize for the delay in getting started. So our last speaker this session will be Leslie New. She's a professor of mathematics, computational science, and statistics at Ursinus College. So I guess go Bears, huh? Yeah. Her interests are research in statistical ecology and assessing population consequence of disturbance, which happens to be the subject of her talk. So that works out well as well. You've also mentioned that you like to incorporate Star Wars into reading and research.
Yes.
So I'm a little curious how this presentation is going to go. So good luck.
Well, I left Star Wars out of this one, but I do have a whole nother talk about statistics and it being the dark side of ecology if people are interested. So we could go into that later. So yes, thank you all for having me. This is a topic that some of you will be very familiar with in terms of the connections between population stressors and what those impacts may be. And so it's the population consequences of multiple stressors framework. It's known as PCOMS. It got mentioned in our last session. It came out of quite a lot of work. So National academies in particular first developed population consequences of acoustic disturbance. That then had its own working group, became the population consequences of disturbance. And as we've worked on it, we've come to this point of saying, well, disturbance and stressors are different, and we need to account for that. And it's really the stressors that we're interested in, and that really there's no population out there that is only exposed to one stressor. Right, and so we need to account for all of those. And so this is the diagram that appeared in the National Academy of Sciences report in 2017. More recent work by Peter Tyack et al. Have also kind of brought back in that connection between stressors and the behavior. And the idea here is that we have our exposure to the stressor. It influences an individual's physiology and or their behavior, which in turn impacts health. Health is what really drives vital rates, and that vital rates are what drive the population dynamics. And of course, there's interconnections between these. So your health in turn determines oftentimes your behavior and your physiology and behavior also influence one another. And that as one individual may be exposed to a stressor, as you kind of integrate that over a population, again, you're beginning to get an idea of how these stressors can really affect populations as a whole. There's been a lot of work done on this, so I'm going to kind of go through where we are now with the individual responses, some ideas about where we're going. The previous session to this one has gotten me very excited. There's all sorts of stuff that I feel like is connected and very exciting to go with. But when we first started this, a lot of what we had were visual data, right? So people go out, they collect behavior, say from focal follows, from behavioral response studies with acoustic playbacks, and then see how individual animals' behavior changes from that. Visual connections of reproductive events. We see the whales with calves. Can we connect that to the behavioral change? Health data that's been collected to date. So we've heard a lot about the kind of hands-on collection of these health assessments, physically capturing the animals, getting that blood, getting measurements of the body mass, the pectoral fin, all the things that I'm going to use the wrong terminology if I try, so I'm going to avoid. Visual health scores. So we heard earlier from Rob about North Atlantic right whales. They give a health score to the animals when they observe them, right? And so all of that can be used as well. And these data have been really valuable in connecting this idea of a physiological change to health, and then from health to vital rates. And I'll try and weave this in as we go, but this is actually one of those places where I see some utility here in terms of things like the MSI that we just heard about, right? Because mortality, serious injury, is often defined as having over a 50% chance of mortality, right? And so here we're developing models that allow us to say, what is the probability of survival? Right? That's one of our vital rates. And so we can then look at this and say, if we know the stressor and how it affects physiology, how it affects health, we may have some idea of then looking at that probability of survival. I forgot to mention as well, each of these arrows is what we call a transfer function. It's a statistical model. So there's a lot of data and a lot of expertise on many levels that need to go into fitting these. And then bioenergetics, this is one that's been very commonly used for these types of models. Beaked whales, gray whales, a number of other species. And again, the work we heard about earlier in terms of the remote sensing of this could change this hugely. A lot of the information that have been used in these bioenergetic models is older. It's based on captive animals. And so the ability to collect this information from the field and really improve these models, I can see the utility of that. And these have been great because they allow us to go directly from the stressor to a change in behavior, usually associated with a change in feeding. That then health, right, different energetic compact, and again, straight to vital rates. Moving forward, we've got new data sources, and I have new in quotes because they're not new, they're just new to being used in this context. And so the endocrinological data that we can collect, the respiration and heart rate that again, we're beginning to get at remote data collection for, isotope data to let us know where animals are feeding and how that has changed over time, the epigenetic data that we learned about today as well, right? So these really enable us to build out that connection, right? So where we've been previously with the physiological data really hasn't connected to the stressors per se. And so now with these new data types, we've got that ability to better link our stressors to the physiological change and through to the vital rates. And particularly physiological response, so different data that are now available from fecal samples, from keratinized tissue like baleen, has allowed us to get at these exact stress hormones, progesterone for measuring pregnancy, and so again, better informing these links. One of the other things which I think is really important for these models going forward is when you read about them, there's a lot of talk about allostatic load, but we don't actually ever define it. And it's hard, like looking at the human health literature, what is allostatic load, has a definition, what do we define it for these species, right? And if we're going to use this as a metric, then I think that's something that we really need to be discussing with the experts in this so that we know what to be looking at. And something that's really kind of been unstudied is this kind of circular link here between physiological change, behavioral change, and again with health. And a lot of that is the multiple data sources that are required, right? We need to be looking at both simultaneously, that link, and having both pathways in one model. We haven't done that yet, even though we know these things are occurring. And one of the things that could be interesting with this is, again, can we make this connection? And can then we therefore look at behavior kind of as a proxy for that physiological change, if it's that physiological change that we believe is the most important? And the reason why I think this is an interesting way forward is that increased utility of existing data sets. The technology that we're learning about wasn't available 20 years ago, 10 years ago, 5 years ago, but we often have these visual assessments of behavior. So can we continue to make use of that really valuable resource to move forward with our assessment of these populations? With population dynamics, within the PCOMS framework, these are really informed by the individual responses that we estimate. We generally look at stressor scenarios. So we sit there and say, okay, we are concerned with entanglement. What are current entanglement rates? What happens if entanglement rates double? What happens if they go away, right? We can look at the effect of these stressors over time and what that might mean for the population. And they're generally done using established methods. So population viability analysis, individual-based models, also known as agent-based models, and then kind of these Leslie and Lefkovich matrices, these stage and age structured models. In the future, some of what we have to do here is just implement them. A lot of the PCOMS models don't actually ever take this last step, and a lot of that, I think, just has to go with the amount of work that goes into some of those earlier estimations and connections is huge. And so we're often spending a couple of years making the links between, say, a stressor and the behavior and how that might affect health, and we're really excited. And then funding runs out, and so we never quite get to that last step. And so I do think one of the things we need to go into the future is to actually implement these models. Another thing which I think is really important, and particularly thinking about stock assessment reports, is most of our population dynamics models tend to assume that everything else stays the same except for, say, our stressor of interest, or even that everything just stays as it is now. It's constant. So the exact conditions we're in now go into the future 10 years, what do we have? And the truth of the matter is we know it's not constant. And so how do we incorporate that? How do we incorporate the drivers, ecological drivers that are part of this as well? We also really need to think about fully integrating the population dynamic side with the individual response side. And this again came up earlier with this idea of propagation of uncertainty. So if each of those arrows is a statistical model, each of those models has uncertainty associated with it. And how do we bring that forward in an intelligent way that allows us to account for it? And yet doesn't swamp everything, because a population dynamics model that says, well, there could be anywhere from 0 to 180,000 to 2 million, like, it's not useful, right? And so we need to really be thinking about that. And there are steps in this direction. Bayesian models are really great for this because you have these posterior distributions that you get that can be inputs into another model, and so you can propagate it through this way. When we've seen these multiple data sources, again, that's actually a way to sometimes as Rob said, it can give more uncertainty, but can also reduce uncertainty, right? So if we have multiple sources of data, it can often help us understand some of the things that we didn't know from the other source of data. So how do we really incorporate that? And one of the things moving forward as well that I would love to see is this validation of the approach. So I get asked quite a bit of like, well, how do you know that this is working? And most of the time we go, well, we don't, right? We are trying to use this to identify negative outcomes. And if we identify negative outcomes, hopefully that action never takes place. And so then we don't know if our model was correct and what it would have predicted as being bad because we never did the model. If the model predicts that everything will be fine, then we could say, okay, we could track going forward, but then we run into that same problem of we said everything would be fine, given current conditions have changed. So if our conditions have changed, then we still don't know if our model is right. And I do think that there's a lot of room to get into historical data here, to really begin to look at whether or not the approaches that we're taking are in fact doing what we hope that they are doing. And so here with the historical data obviously would be needed on the stressors that these animals are experiencing. We need some historical data ideally on abundance because we're looking at population dynamics models, reproduction, but we can get at a lot of this information both from historical records, but also I'm involved in some work at the moment that again is looking at baleen. And so going back into museum collections and looking at these collections back from pre-whaling, whaling to now, and saying, what do we learn from these data? Even if we don't know the exact population, then I can still look at the relative change and see if the relative change that we predict in the presence and absence of certain stressors puts us relative to where we might be now, and really get an idea of the potential sensitivity of how these things might react to different components of the data that we have available. Something else that I don't have up here that I haven't talked too much about is the interaction between all of these, right? So with multiple stressors, they also don't just influence an individual on their own, but understanding how these interactions take place. Are they synergistic? Are they antagonistic? Do they actually not involve at all? This is difficult in human health studies. I can't even imagine the complexity of what it's like to try and do with the animals that we've talked about today. And so, really getting at that as well as another important kind of component and direction to the PCOMS models. In terms of using PCOMS, so a lot of it has been used for this idea of management and conservation. Where is the population now, right? What is it doing? Environmental impacts assessments, right? So people want to plan to do something, they need to do their EIA, PCOMS can conceivably be used for that. And then of course, what we've been talking about today is stock assessments. And so this isn't actually an area where the models have been used over much, but I do think, as I said, there's room for that here. So if we think about abundance, we are in a context where ideally, right, if I go, hopefully this will actually let me go back, right, ideally here, when we're talking about population dynamics, we're starting with a known abundance estimate, right, and then we're moving forward from that. But if we're thinking about our current kind of funding, availability of data, if we have information on past abundance, which we often do, and we have information on stressors from the previous abundance estimate to now, right, can we estimate what we think abundance would be in our carrying conditions? I don't know the legality of using that for an admin, but it does allow us to look at that and allows us to look at the abundance in the future. So again, thinking about things like the Deepwater Horizon, where would the population have been if, and I know this is something that's being looked at, which is why I'm using it as an example, where would the population have been if in fact we hadn't had that spill? And that helps us get the mortality, serious injury, and again, in part through that abundance. The mortality and serious injury, again, that I already mentioned in terms of that health, but also thinking about like with the methylization and the age and the context, right? So we know that the context of a stressor can be really, really important. And so if we are able to take some of these new data and say, okay, we now have the context that this animal is experiencing a stressor when their biological age is less than we would expect, well, the impact of that stressor is going to be different than an animal that would be more its actual age and biological age might be better linked. So again, how can we use it to inform those? And then population trends. So again, what might the population trend be into the future, but also looking at that past data and saying, if we can get at these population dynamics, where are we going from there? Are we seeing an indication of a trend? And that's part of why these models got developed in the first place, was this idea that normally we need like 30 years of data to say, oh, look, the population's declining, oh no, and it's too late. And so a lot of these models got developed with the idea that we could understand more faster, and therefore understand more about what is going on. While my name is the only one that is on this slide, it took a village to get here. I'm just not willing to put people's names on slides that they haven't seen because they may not want to be associated with it. I have tried to include up here pictures of everyone who was on the first PCAD working group, as well as the current PCOMS working group. I'm sure, in fact, I realized as I was sitting in the chair that I know I've missed people. One of the glaring ones is John Harwood, who was the driver behind this, but he's been very cagey and managed to keep his photo offline. So the only photos of John Harwood I could find were not him. So he is not here. Same with Dave Moretti. I guess maybe the Navy doesn't let him. Very difficult to find his photo. And certainly with regards to the funders, I've included the funders, Office of Naval Research, National Science Foundation, Marine Mammal Commission, who I have received funding from. But I know that many of these individuals have received funding from other sources as well, including things like CERTIP and other sources. So none of this would be possible without all of these people, and certainly without the dozens, if not hundreds of others who have been collecting the data that have been used on these models. Thank you very much.
Thank you very much, Leslie. I was wondering if you could all help me give a hand to all the speakers of this session that we've had. And I think perhaps the best thing for our schedule is we'll go ahead and take our scheduled break now, and then in a half hour past, we'll go and begin our panel discussion. So thank you. Wonderful, we're on the record. Thank you everyone for our afternoon panel discussion on innovative and integrated quantitative methods for assessing populations. Unfortunately, we didn't have a chance for open questions for most of the speakers, so I thought we would start by just opening up for informative questions from the commissioners and the scientific staff. Sue.
First, just a thanks to all of you and you up there, Rob, because all the presentations were really, really excellent. But I have to head to Kate because of that amazing array. I mean, I was just telling John outside, just looking at the number of instruments you've had out makes me tired. I mean, deploying all those and getting them back, and so just congratulations to you and the whole team in terms of the data you have and the publications you're getting from it. So two kind of really quick questions. One, excellent work on the odontocetes, but do you have mystacete data, especially Rice's whale? Are you going to be reporting out on any of that soon?
Yes, okay, so thank you. I appreciate that recognition. Yes, we have data on Rice's whale. This study that I talked about today was kind of 200-meter isobath and deeper, but this last summer we picked up a bunch of instruments that were sponsored by the U.S. Trade Representative Office that went all the way around the southern Gulf, kind of in that band where we think the Rice's whales are, and we've been kind of strategically deploying some instruments in the northern Gulf as well, in areas that have been identified as probable Rice's whale habitat, so we're bringing all of that together. And should have something to say about where they actually are distributed next year.
Okay, Peter?
Well, I'll just ask the question I sort of gave Leslie to anticipate, which is you've presented, I mean, people looking at these models really have a hard time relating them to the actual species and situation. So I'm just curious, I know there are folks in the room who've worked on specific species and specific elements of that. And do you want to give us at least a sense of how they're being applied or have been applied for some relevant species?
Sure. So the PCOD, PCOMS models have been used for quite a number of species. So one of the main interests for them initially was beaked whales, right? And just the effect that acoustic sonar, particularly from the Navy, may be having on beaked whale species. And so really getting an idea of, again, that initial response. So like the Autech Naval Range was huge in informing that, because you've got the hydrophones recording call rates, beginning to get an idea of how animals leave an area, come back. Some information, obviously, on the sonar sounds from the military. You know, some of it, you don't get all of it, but it's there. And so then being able to connect that to, in their case, the interest being in around mass stranding events. And so the framework itself, a lot of it has been applied to species where there are a lot of data, because that gives us the ability to kind of initially say, what are the connections we can make, and what sort of information do we need to get there? And then the next step is going to those species of particular concern, who do we need a stock assessment report for this year, right? And then saying, okay, they may not have the same type of data, but now we have an idea on how this works. North Atlantic right whale, again, another species that was one of the first that was used with the framework. Again, it has a lot of data and is of concern in terms of the entanglements and the ship strikes.
Lori?
Actually, I have a follow-on to the rhesus whale question because it got me thinking about things. Number one, do you have any I know that they've been struggling to, like, how are they going to get abundance estimates for them because it's such a small number, but they do have biopsies from, I don't know, practically all of them, or a good portion of them, and photo ID data and tagging data. So have you guys thought about this integration of different data streams and how acoustics could play into that? And then kind of related to that is, I know there's thoughts that there's different, there's the east winds and the west winds, and could acoustics help to understand whether those are the same animals or different groups of animals?
Sure. So have we thought about combining the data sets? Yes. The thing that's a lot harder with baleen whales and passive acoustics is that the detection ranges are much larger, right? And so estimating that area over which you are able to detect the animals is difficult. And also getting the Q rate right is difficult, right? So we don't have a great Q rate for these animals. In fact, every time we tag one, it shuts up. So we don't have a great estimate for how to convert between call counts and animals yet, but I think we can get there, and the way we're getting there is through tracking. So Melissa Saldivia has put out these wide aperture arrays where she can see a calling animal move through the array, and from that I think we can get decent Q rates, and we can solve the detection range problem with some propagation modeling and that localization information. So I think we will get there. Yes, there are already, we already know that there are differences between calls between the east and west, and so that does indicate that there are probably there is some separation between those populations, and there are some calls that are very distinct, right? They just stand out as, I think they have special names. I haven't named them, but this one has a hat, right? Acousticians do this. And so we may be able to determine whether those are linked to actually individuals, but I think the jury's still out on that.
Since we're on the subject of detection ranges, can you clarify what you think the detection range for beaked whales is in the Gulf of Mexico from your data?
Yeah, probably maximum 3 kilometers and more like 2 kilometers most of the time. Yep, very close.
Peter? Oh, Andy, go ahead.
Thanks, Aaron. I've got 2 questions for Jeff. One is procedural, and that's like how what you presented is going to play out with the stock assessment for those and the TRT. So that's pretty straightforward. But also, like, what other species do you think are amenable to that approach? I had some thoughts, but I'm kind of interested in what else you were thinking about. applying that approach to. And nice to see you too, by the way.
Yeah, thanks, Indy. Yeah, procedurally, you know, getting these values into the SARS is straightforward there, right? I'm going to be working on writing this up to be published in some form or other, and then presenting that at the SRG meeting next spring, and hopefully getting new numbers into the stock assessments for those draft 2026 stock assessment reports. The TRT process is kind of a weird one out here on the West Coast. I'm not sure how plugged in you are to the details and nuances of that. Yeah, I won't comment too much on that. The aspect of the process that's facing us imminently is to deal with the sablefish fishery only. And the work that I did, that I presented today, doesn't apply to that at all. My understanding, I think, is that the TRT scope may broaden then, you know, or there might be a different TRT, or I'm not even certain. So in the spring, and so if it does and addresses, you know, Dungeness crab fisheries and others, then presumably these numbers would be able to come to the table there. But yeah, there's still some questions there as far as like how NOAA's going to kind of do all that. As far as like other species or stocks that this approach could be amenable to, I mean, generic answer, right, would be anything for which there are repeat reports of individuals that can be identifiable as such. On the U.S. West Coast, you know, we get the same kind of data for blue whales and gray whales, for example, although the sample sizes are a lot smaller. And I think in the case of blue whales in particular, the identifiability is probably not quite as clear. I don't know, you know, for East Coast applications where that might be, but I do, you know, I have had some discussions with some of the national stranding coordination meetings where they had been aware I was doing this, and then they were asking questions like, should we be collecting our strandings data a little bit differently? Because I guess there's a tendency to, if they get a report of, you know, like an entangled animal, and then there's another event, and they know it's the same animal, they just like there's certain information they just don't include, so that traceability to generate encounter histories isn't there. So I would, you know, suggest for anyone who's designing their, you know, level A, level B, you know, recordings protocols to, you know, get those repeat reports on anything that is identified as such, and attribute individuals to individuals, so that maybe you could do, you know, you could do the same kind of thing. You said you had maybe some of your own ideas on that. I'd like to hear what those are.
Well, I was just thinking, you know, we've been working really hard on the East Coast to think about unobserved mortality. You know, some of Pace's work, and just for right whales and humpbacks, for example, would be really interesting just to apply the same approach.
So I'm curious, you know, right whales, you guys have so much more information about right whales. You know, it seems to me, and this is probably an exaggeration, that the fate of like almost every animal is kind of like known to individual. And I kind of feel like the approach that I've been applying here is sort of a kind of a data poor approach, and that you could probably do more than that with right whales.
I'd kind of like to hear what Rob has to say about that, because I think the fate actually of a lot of animals is poorly understood, and we have a lot of animals that disappear that eventually are assumed to be dead. But Rob knows the data set much better than I do.
Yeah, I'll try to address that, and then I'll actually try to go back to Lori's question too. I think basically, I agree with you, Jeff. Like there is a ton more of information, but there are also like there's a huge amount of sighting heterogeneity, in between sort of resites. And so, it basically like having to have more sort of information on the resite and also on possible movements following last sighting, I think is going to be key. I think Enrico and Len published a paper last year, 2 years ago, that was specifically about mortality from tags, but that sort of the approach that they had in there might have something to sort of inform on entanglements. I just had a quick response and thought, but from the right whale world, for Lori's question about detecting it or sort of detecting and identifying individuals in acoustics data, at the right whale meeting last year, Irina Tolkova, who's I think a postdoc at Cornell, had presented some analysis of acoustic data, both from DTAGs, but also from the array. I think they were using one of Dan Zitterbart's array. And they think it run through BirdNet, and we're looking at sort of doing a sort of multivariate, multidimensional sort of clustering. And the DTAG data were much clearer in terms of being able to use the acoustic features to tag that to unique individuals, which of course they knew because they put the tag on. But there was a fair bit of information in the array data as well. And I think she has a paper on that on review right now. She didn't include the array data because there's a lot of overlap, but there may be something there with decent arrays to sort of try to tease out adding some information in.
Randy Reeves has his hand up.
Yeah, in that discussion between Andy and Jeff just now, it occurred to me that surely humpbacks in the North Atlantic would be a great entity to try your method on, given the long time series of observations. And Danielle probably knows a lot about whether it's would be amenable or useful to try that on there, but I'll let him speak about that.
Go ahead, Jason.
Following on the right whale entanglement stuff, maybe I'm wrong about this, but I thought that PACE actually did some kind of a multi-state model where entanglement was a state, and you would estimate transition probabilities to, remaining entangled, dying, or becoming unentangled. And I was thinking about that when you were talking, Jeff, but I realized that the observation process for the resighting of entangled whales and like the happy whale sightings is probably so different that it wouldn't work. But in the right whale context, you probably could do a multi-state model, right? Where you could estimate all of those probabilities.
Yeah, I don't have too much to comment on there except to say yes, I know Dick Pace worked on that. Now Dan Linden is, I think, kind of like picked up that torch a bit, and he presented on that. I saw him give a talk just a couple weeks ago, and so yeah, I think, but I just recall that, it's a fairly complex model, and it was still embedded with lots of assumptions, some of which he considered to be problematic. So I think it's not a case is not closed yet.
I just had a couple specific questions for Rob Schick about your modeling approach. We only had a brief glimpse at your likelihood function, but my impression was that you're assuming that the observations were statistically independent. So in other words, call detections were statistically independent based on the use of the Poisson model and the form. How do you test that assumption, and what effect would a violation of that be? So, if a whale does calling bouts, for example, which wouldn't be statistically independent, how does that bias your estimates?
That's a great question, and I don't have an answer for that in terms of how it would bias. It's something we talked a lot about when trying to set up the sort of snapshot, just because I have two thoughts for you, and it's a sort of unsatisfactory response, I realize, but we wanted to sort of ping or sort of like bias off of the aerial survey data. And so basically we chose each one of the transects to be conditionally independent. And so then we're thinking about like, okay, if we have the duration of that fixed, then we're only going to look at the duration of the calling data. knowing full well that there's huge amount of deal variation, let alone individual variation. So it's a great question, and I don't have an answer for you, but it's something that like it would be really nice to be able to sort of tie together, because also we've done it is like we were doing calls on the hydrophone, and it's just calls. We don't know if it's like one whale calling a bunch in bouts or if it's other whales sort of calling back and forth. So there's bias in both of those, and I don't have a satisfactory answer for you. Good question.
Okay, thank you. Not to put you in a hot seat, but kind of a follow-up question. And one thing I always wonder when you're trying to integrate various data sets to decide how much you're weighting the data. You know, sometimes you weight by your perceived uncertainty in the data. In your case, how do you weight the relative contributions of the visual sightings and acoustic detections in the results you presented?
Well, numerically, I don't have the answer for you, but in terms of like how, like visually, when we look at, one of the things we did in the paper was to fit it. So we fit it jointly, as I talked about. And then for the one day that we had a full sort of complement of the aerial survey data, we fit the model just for the hydrophone data and then just for the aerial survey data, so as if it was just sort of standalone models. And actually, interestingly, the acoustic data, assuming we have faith in our estimates of that call rate, do a better job on the abundance than the aerial survey data. However, the sort of spatial distribution of them is pretty even, as I think I tried to mention a little bit, the sort of that sort of softer ones. So in terms of what we've seen so far in the real data, but then also in simulation, the aerial survey data do a better job estimating sort of the spatial patterns, whereas having the acoustic data and help tie in the abundance better when they're both contributing to that.
Okay, thank you. Dee?
Thanks, Aaron. Yeah, my question is for Jeff, and kind of following up on some of the comments with that Andy had. I was curious. Well, one comment. I don't know. You might already be aware of these, but the Center for Coastal Studies does have a database of re-site information of entangled whales. So it's right whales as well as other large whales. And they keep a database with the repeat sightings of the same individuals. And I know Ed Lyman also has a similar database for the humpbacks, and he gets the Alaska data as well as the Pacific Islands data, and tracks the individuals over time. You might already have incorporated that or be aware of those data sets. And I was curious. Maybe this isn't even a factor since it's based on resites of individuals, but does it matter the gear type? I'm thinking more like a pot from the Aleutian Islands, you know, for king crab versus a Dungeness pot, or, you know, you're talking about fixed gear. If it's just a single pot or a trawl of pots, is that going to play into this, or is this more based on resites of individuals?
Yeah. So there's what I would like to do and what I think I can do. Yeah, I mean, for sure, I would expect to see all sorts of heterogeneity in affecting both parameters of the CGS model, the availability parameter and the sighting rate, conditional sighting rate parameter, as a function of, you know, severity of the entanglement, type of gear, et cetera, et cetera. I haven't tried to explore that, but right, I don't expect it would be a fruitful exercise, just given the few number of individuals that are recited. It's enough to get estimates, but just as a reminder, out of 175 cases, I had 18 individuals that were cited, you know, a second time or more, and then of course most of those are only cited 2 times, not additionally. So I think trying to understand how those parameters would vary as a function of, let's say, gear type would be probably not estimable with the data set I have. That being said, it's the vast majority are commercial Dungeness crab pots, so it's not like I would be looking at a bunch of different types of fisheries that are significantly contributing to the data set. But I mean, it's a really good question, and I don't think I can get at it right now, but hopefully I could one day with more data, or I could explore it and see if I get lucky. Good question, though. Thank you.
Aaron, go ahead, and then Karen.
That was very similar to my question, and I wanted to add some thoughts. First, I have a question. Are you considering resites of the same individual, perhaps gear-free, to extend an individual sighting history? And then two, I was thinking less about gear type and more about entanglement severity. And of course, you know, if the wrap is around the mouth, that's really severe. And so you could, just for a very first pass, look at the animals that do have resites versus the animals that don't, and see if there's a difference in gear type or in entanglement severity among those.
Yeah, for sure. Good suggestions. I think, can you repeat the first part of your question?
The first part is, do you have opportunities to include a sighting at the end of your sighting history of an individual without gear?
Right. So these are, by and large, not animals with fluke IDs. So while we can say that, okay, this entangled animal is the same as that entangled animal, if that animal were to shed its gear and then you saw it again, you wouldn't know that you were seeing the same animal necessarily. That's accounted for in the detection rate, because the availability parameter is essentially the probability that the animal is staying in an area where it can be observed and is still alive and still has gear on it. So if you think about the detection process of animals that you might not ever see, one reason you might not ever see them is because they shed gear before you see them, right? So that's implicit in the math. Now, that being said, there are maybe about a third or so of the individuals do have individual fluke IDs. And those animals tend to have sighting histories before they're entangled and not have a sighting history anymore after they're entangled. So I haven't formally analyzed that piece of the question to, like, let's say, estimate like a survival rate for entangled animals, but it does appear that animals that become entangled, for the most part, disappear.
Karen, did that answer your question?
No, I just actually wanted to follow up on Dee's suggestion, and Jeff, I should know this because I reviewed your manuscript, but along the West Coast, you're right, most of our fisheries that entangle whales are single trap or pot that the whale can swim away with and can be entangled with for months or even years. There are a couple of fisheries that are more likely that are multi-trap systems that would anchor them, like spot prawn and some of the longline gear, that the entanglements are less common in. Are any of your cases, or if you excluded those, or did you exclude those, just because it seems like especially spot prawns, if they're entangled and they don't get disentangled, they will just drown and disappear and no longer be available to be seen. And it would be interesting if you didn't exclude them up front to see whether that would change your numbers at all if they were excluded.
Yeah, I did exclude quite a few fisheries. Commercial spot prawn is still in there. There aren't very many cases that involve them. It's like maybe like, I want to say like 3 or something. There's not that many. So I would need to look at how things might change if I exclude that fishery in particular.
Peter?
Yeah, again, I have a sort of, again, naive question for Rob. Really appreciated your presentation, and I'm really asking about the follow-on for this work. We have, since the date of those analyses, we have a lot more passive acoustic measurements going around the entire range of North Atlantic right whales. We have the continued survey effort. Obviously, the Cape Cod Bay is an area of concentration of both efforts to develop the model. But where does it go from here in terms of our understanding, both of population assessment, but other values of the modeling?
Yeah, thank you for that question. I think so. One is that an issue of funding to be able to sort of apply it to other areas. And with the aquarium, we have a proposal into RWSC, I think, and as part of that to look at the southern wind energy area, if that's still the appropriate acronym. But basically to do, because there's a whole bunch of aerial survey data that the aquarium did and a whole bunch of past acoustic monitoring data. And so that would be a really sort of easy first place to try and do it. So, and we've talked with Laura Ganley at the aquarium a bunch about that being sort of an obvious place. I've had a few discussions with Anita Murray, if I'm remembering correctly, at the state of Maine, because they got a bunch of Section 6, I think, money to sort of put out a fairly broad array, and do aerial surveys as well. And so that would be a sort of next obvious place too. So we're sort of game and interested in sort of extending and seeing if the model can be useful in other places. I think kind of getting back to what Andy said about sort of uncertainty, one key aspect would be sort of just sort of careful discussion and consideration when we're considering those areas. Well, what are the assumptions and the sort of features of the Cape Cod Bay data that we were able to lean on would have to be sort of considered and maybe changed in other areas in terms of like things like, you know, either acoustic detection or aerial detection. So that's one. And then basically the model that I mentioned with the sort of zooplankton add-in, we have, just because of all the work that Cape Center for Coastal Studies has done for so much, we have a lot of those co-registered days where we have aerial data and PAN data and zooplankton data. And basically sort of hopefully that not by the end of this year, but totally by the end of this year, we will start to flesh that out with that one existing data set in Cape Cod Bay. So going beyond just sort of kind of a sort of proof of concept for the stats literature to try to make it sort of a more interesting sort of summary of all the data that have been collected there. But in terms of other areas outside those in the right whale world, I mean, again, as I touched on the slides, like where there are sort of co-registered, you know, PAM arrays and line transect data, like it's definitely worth trying.
Has Canada expressed any interest in pushing this in the Gulf of St. Lawrence?
No, I've talked to Adele Labe a few times about it, but I would sort of haven't sort of heard any more sort of specifics about it. But I think hopefully I'll see her at the Right Whale meeting next month, so I'll ask.
Well, I'll give Robin a chance to ask a question. Go ahead.
Sure. Yeah, this is an online question that I think is for Leslie. The population consequences of multiple stressors model is an amazing tool to possibly get an outlook of what's coming for many species. It was mentioned that not many have been finished because variables can and do indeed change. However, I'm wondering why we aren't running multiple scenarios for a species and giving predictions based on each of those scenarios. Is this possible, and what are the reasons for not doing it if it's not?
Thank you. So yeah, it's definitely possible. It's been done for some species. Blue whales was an example where we looked at some of that. And I think, again, a lot of why it hasn't been done comes down to kind of timing, and where as statisticians we get excited and don't do that last step, because sometimes that last step seems very, very straightforward. But it is doable, it has been done, and I think that one of the things we just need to think about in terms of actually using the approach is that last step is an incredibly important one, where to date a lot of my work has been in developing it and how do we make it work, and so we focus on those components where we don't know yet how we could make it work. And I see Rob's hands up, so I'm assuming, given that you've been massively involved in this as well, that he's got further things he'd like to add.
Just one quick thing to add. There have been several of us in this sort of virtual and physical room there who've been working on the multiple stressors project that Peter Tyack has led. And as part of that, Enrico Prota he's written several papers on this, but one of the most recent one that's in review does exactly that sort of scenario testing and sort of what would happen, sort of no entanglement, better prey, worse prey, et cetera, and also some of the interactions of those. So I think I don't know if that's been accepted yet, but it's definitely in review. So that's a place to look.
If I can make maybe a follow-on question on this, which was touched on before, it seems like one of the values of doing these integrated models, like the multiple stressors, PCAT, PCOD, it gives you some insight about sensitivities and maybe data gaps. Given that, what data, and it probably depends on species, but in general, what data do we know the least about that gives you the most concern in these models that you would prioritize for collection or addressing to reduce uncertainties in these types of models?
That's really hard because I'm trying to think, I mean, for all that we talk about it, I don't think we've done like a formal sensitivity analyses over the multiple species that we've studied. Certainly, I feel like one of the spaces where the data are very new is around that physiological change component. And again, new to us. And I think that there's a lot there, given this focus on health and allostatic load, that is really worth building out. And so taking advantage of the new technologies, right, the hemotag, I can see amazing uses there for animals where we can't get blood samples now. And just being able to fill in some of those gaps about like, what is the stress? How do we put things in context better, right? Because we've definitely found over a number of the models that the context of the stressor is very, very important. And so how can we fill in some of those gaps? And then I think for individual species, a lot of it's going to be what type of models are going, what type of data can be collected, what types of models that we've done are available for that, and then kind of identifying what would be needed in that situation to make it work. Because again, what you would do for a beaked whale versus a humpback whale, obviously going to be really different.
Francis?
Sort of a follow-on to that. I mean, as far as I'm aware, most of the species that you've worked on have been ones where there are like major conservation or political sort of concerns around, and you're using the model to get at some of the parameters, actually. So I was wondering about instead sort of a comparative approach of taking, for example, harbor porpoises in the North Sea and the Atlantic or in San Francisco Bay Area, where you've got different populations where a lot of the vital rates are known, and then you have different stresses. And you could feed in sort of exposure to PCBs versus malignant bottlenose dolphins versus wind energy, and then you could build those and then use them as a sort of comparative and see how your model was essentially working in those different areas.
Yeah. So I think that would be really, really valuable, and certainly thinking about things like the bottlenose dolphins. So the original kind of PCAD working group identified elephant seals, bottlenose dolphins, right whales, and beaked whales as the things to study, because different life history strategies, different data availabilities, and then different levels of concern. And so particularly, I think with the delphinids, where we can get a lot of that detailed health data, definitely opportunities there. I have also been in discussion with a couple people. I don't know what will happen with this, but my current postdoc, his PhD was originally supposed to be a comparison of northern and southern right whales. And so we've actually discussed what it might look like to try and do that with those species, and like, especially the southerns, with the kind of all of the southerns, the North Atlantic, even say, okay, if we can do it for that, can we then learn something about the North Pacific, where we have almost nothing, and really get, if we believe that these are animals that should have very similar kind of life histories, but are obviously very, very different, what are the stressors that are really getting at it? And for North Atlantic, we know some of it is just they're in such an intensive, human-developed system. But with the southerns, again, there's so many different stressors that the different groups are facing that I think we could conceivably begin to tease it apart. So it is work that we'd like to pursue, but that requires me to finish writing a grant.
Go ahead, Lori.
Just following on to that and along that line, do you feel like, I mean, like you say, early on, we concentrated on elephant seals and bottlenose dolphins because we had data there to get at those transfer functions, specifically like exposure to physiological state to health or whatever. Do you feel like there's things that have been learned from that can be extrapolated to other species, or, do you feel like that they're going to be so species dependent that it's not really going to be that useful?
No, I mean, I think there's definitely things that we've learned in terms of, the use of the bioenergetics models, for example, right? Like that was actually something that got brought up numerous times during the first working group, that because of many people's focus wasn't initially looked at closely. And then as we began to use it, realizing the utility of it. And so just the fact that they became a focus when at the beginning of those discussions, it was very much like, oh, well, those, I don't know, right? And instead, it's become, I think, the most commonly applied approach. And I think the other thing as well to kind of think about for us is that things like North Atlantic right whale, they're so data rich and give us the abilities to do things that we can't do with other populations. And so I think some of what we've learned is what's possible and what isn't, and what levels of data. And I think the next discussion is, where can we get those data? Do we have to have those data? What are the sensitivities as we take those data away? And that will help us understand better, again, which populations and where. And certainly with the PCOMs, we're in a similar situation. And again, Rob can speak more to this because I've not been on that working group, but like the gray whale work that I am part of, which feeds into that, we're doing it on the gray whales in part because we have a lot of data on them. So we can get information on multiple stressors, we can get health measurements, we can get some of the physiological measurements, and so can it work? As opposed to it being a species, well, again, changes obviously happening now, but at the time, not being a species where there was concern or the need for the updated SARS or anything like that, as much as it being ooh, we have the data. So let's see where we can go with it. So Rob, I'll toss it over to you as well.
Yeah, I think and I actually think Rico's original sort of structuring of that gray whale model actually was, just sort of taken from, or sort of inspired by some of the right whale stuff in terms of using the visual health data, which is cool. I wasn't involved in that part of it. I think maybe if I can sort of touch back on what Aaron asked about the data, but specifically thinking about right whales, the going cross or transboundary was a bit of a challenge, just in terms of like what data are collected by what agency where, and being able to get them and then assimilate them. Phil Boucher, who's now at BIOS in Scotland, did a huge amount of that work, and that was a challenge and didn't always sort of line up once you sort of cross boundary. So that was one. Another one that we struggled with in the PCOMs was noise, to sort of think about like, at what scale do we collect the noise, or ambient, for instance, and then what scale is it a stressor, and like what is it sort of operating at? Is it something that's just going to cause a right whale to be quiet, getting your question to me about variability, or is it something that could ultimately be tied to a vital rate? And sort of thinking through those scales for the right whales was a challenge, and I'm not sure that we satisfied that well. And the last one I'll say for right whales again is prey data. So a lot of the sort of broad scale, and Aaron's on the panel, she could probably answer this better than I can as well. But the sort of the broad scale sampling that's been done is through things like the AZMP project in Canada or the EcoMon project in the US. Like those are both collected. They have different, different sort of protocols. They're amazing. They don't necessarily line up spatially with the sort of the full kind of transboundary distribution. So that's a challenge too, to sort of think about like, what do we have these data at in terms of the species side, and then what are the stressors at, and are they overlapping enough in space and time to sort of answer these questions?
Aaron again.
I'm just going to add one more bummer to Rob's list. And I've been kind of at the edge of the PCOMs activities, but right whales, the North Atlantic right whale, which is sort of the best case scenario in terms of data, something that does come up in the power of these PCOMs models is there's only 372 animals, right? And so there's a tremendous amount of individual variability, and we only have, 600 historically reasonable sighting histories. And it's really just not enough to statistically estimate all of these different parameters, from the health to the entanglement to the prey to the demography. So as rich as it is, it's still really data limited.
Okay, Rob is nodding agreement on that. Peter?
Yeah, I want to go somewhere totally different that I don't know anything about, which is, Kate, your depiction of odontocete ecology and use of the Gulf was just, for me, mind-boggling. It's kind of like the eDNA picture this morning of the west coast of California. I'm just curious, I'm not an odontocete specialist. Going from individual behavior to that kind of depiction, where is this taking us? I know Andy Reid studies odontocetes, for just to bait him a little bit. What is this telling us about odontocetes, or do we already know all this and this is the first time I ever saw it in terms of their use of ecological areas and differentiation like that for understanding beaked whales and other toothed whales?
Well, it's new to me too, so you're not alone. Yeah, I think for these offshore species, we haven't known a lot. And these large-scale patterns linked with oceanography, even that kind of very gross level of information is pretty new to us. Andy and I have additional data collection on the East Coast where we see echoes of these same patterns that we're seeing in the Gulf, and having that whole story kind of stitched together, I think is really powerful and starting to help us understand these whole populations much better. And maybe Andy can comment on that as well.
Andy, you have your hand up?
Yeah, thanks, Aaron. I'm scared to weigh in here because Kate knows more than I'll ever know. But part of the issue is we can't discriminate those species using passive acoustics right now. Like there's a whole, where we work in Hatteras, there's a whole community of small delphinids that we can't discriminate. And so trying to understand species-specific responses and trends is hampered by just basic detection, basic classification, essentially. So there's some fundamental work that needs to be done there so that we can understand, like, okay, what's happening with striped dolphins and how is that different from pantropical spotted dolphins? We're not able to do that yet. But I also just acknowledge the enormous amount of work that Kate and her colleagues have put into the Gulf, and I'm humbled by it. It's really remarkable.
I'll follow on that question about the Gulf work. I mean, it's a huge effort to put in all these recorders and get the data analysis. But one thing I always wonder when you're trying to detect Odontocetes signals on this scale is that your detection range is so low, so the effective area that you're monitoring is tiny, you know, a fraction of a percent, like 1 to 10 to the minus 5. So I'm sure this was a question you thought of deeply. What steps do you take to ensure that what you're seeing is not just the displacement of animals moving to some other area versus a change over time or a trend?
Yeah, that's something we've wrestled with a bunch, right? Like in the worst case scenario, you picked a canyon where a beaked whale likes to live and they live there full time and you decided that was your hotspot, right? That is kind of the extreme of that argument. And so I think, and that was why when we had this small set of sensors in the Northern Gulf, we really weren't ready to extrapolate that past, you know, okay, here's some points on a map. But I think now that we're getting to this coverage and we're seeing this consistency in sites that are located, you know, 1 year here and 1 year kind of neighboring, and we see the same things, and we're starting to see these relationships with these large-scale oceanographic features that are moving by, now we're starting to get that feeling like, okay, we're really observing the variability that we expect. But there is a lot of local patterning, and so clearly we can't just rely on one sensor, right? We do need an array, and we need to compare those locations over time. Yeah, I think we're starting to believe our data more, but you know, the truth is always in the middle of what you think. It's not a perfect mixing pot where everything's evenly distributed, and it's not hyper-local. There's some kind of medium truth there.
Is there tagging data from beaked whales to get some idea like what the lateral foraging area they have is?
Not that I'm aware of for the Gulf. There was some good sperm whale tagging data from the late 2000s, I want to say, late 90s, the Swiss study, which showed some good kind of ranging over pretty wide areas, but it would be nice to get more species tagged for sure.
Okay, thank you. Robin?
Yeah, there's another Zoom question from Alexandra Curtis that's probably for Jeff. Rather than excluding multi-pot entanglements, might those or the serious injury determination value be modeled with a two-class heterogeneity coefficient? If this converged, it might reduce the estimate for overall probability of detection.
Alex, we'll talk about this in the lab tomorrow. She's in my program, and I think she's being cheeky. But yes, it's a good idea. You always have good ideas, Alex.
Jason?
Okay, I'll swing back to PCOMs and gray whales. So Aaron said that the data were too thin for right whales, even though it's really good data. And then you've got gray whales, which are much more abundant, but maybe you don't, clearly you don't have the same kind of precision, individual sighting histories and stuff. So what do you think the prospects are, given the disruption that we're going to hear more about tomorrow that's recently happened with that species, for gaining insights on some of these transfer functions between maybe, food availability in the Arctic and health and behavior and how they respond by going to new places? Do you think that there's a lot of potential to, one, focus in on the data gaps that would be most important to fill, or even maybe at this point start to estimate some of those important functions?
Yeah, so I think, and this is something that we run into in a couple, I think, of the PCOMS case studies, is kind of what I would refer to as large P, small n, right? So the actual sample size is low, but we have a lot of detail on every single individual. And that's something that pops up, for instance, in genetics work a lot of times, right? You take the genome of one person, you have 1 million data points, but your sample size is still 1. And so that's obviously not the problem with a lot of other species. And so it's that balance of figuring out where does having a large population but less information on each individual help us, because that variation component we can get out a little bit more. I will say with the gray whales, the work that I'm doing is specifically on the Pacific Coast feeding group. And so how much of that is extensible to the broader population, I would defer to the people in the room, because whatever I say, I imagine is going to be wrong. But I do agree with you, like part of what we've been doing with this is testing out, like, what do we think can work? And I do think we need to get to a point where, right, with these questions, let's try something and see, right? And if what we fit is completely off base, then clearly, right, it's not working. And I think, as biologists, as marine scientists, absolutely we've come up with results where we look at them and go, that's just not biologically feasible, right? And so I think it's worth sitting there and saying, here's everything that we've learned. Here's the situation for which we need, not answers, because our statistics doesn't give answers, we just give information, but we need something. Let's try and do it, and then see, and hopefully have it be useful, see if it's something that serves the purpose.
I thought I'd ask a question, try and link with some of the previous sessions. So we've seen some new technologies emerging, such as using satellite imagery to detect whales, work in eDNA. Clearly, these technologies have a way to go, but they're already showing quite a bit of promise. Do you feel that these technologies can be integrated into these existing integrative models, or is there some further theoretical work that needs to be developed? Like eDNA has this time lag associated, for example, that I don't know if requires fine-tuning.
So, I mean, I think to a certain extent, so from a statistical perspective, I would say that the approaches for integrating multiple data types are there, and then it's kind of what's been discussed quite a bit about that careful thought about the variation, about uncertainties, about how it may bias it, but that again kind of comes down to those kind of biological questions as opposed to theoretical development. And so obviously, I don't know a great deal about those individual technologies, so the people who discussed them might have very, very different feelings. But I feel like if the people working on them feel that they're kind of ready, then I think there are absolutely ways that we can pull it in, and then I would kind of rely on those experts to tell me where they are in the process to make it something that they'd want to see incorporated versus something that's going to add so much more uncertainty that it's not helpful yet at that stage.
Okay, I'll ask another kind of general question to the entire panel. In terms of these stock assessment reports, there's a variety of metrics people want to measure, from abundance, serious injury, and mortality. I'm guessing that was a small subject you were talking about there, Jeff. Stock structure, population trend. And I guess I've always wondered if there's a kind of a hierarchy in goals here. I mean, we want all of them, but are some of them more technically achievable with others require fewer assumptions? Just to give my bias, I've always seemed to me that maybe measuring population trends might require fewer assumptions than measuring absolute abundance, at least for acoustics. And I was wondering if you guys had some thoughts about, whether there's this hierarchy or whether that impression of mine might be true.
Yeah, for sure. I mean, trends are easier to get at, and I think when you look at a lot of the methods being developed, particularly for passive acoustics, I think that's generally considered to be like the lower hanging fruit. Like we think we can get to trend estimation spatially or temporally, right? Sooner than we can get to measures of absolute abundance and so on. And so you'll see that, and 100% that's useful. From a strict stock assessment report standpoint, like if I'm reading the letter of the MMPA and doing this with my NOAA hat on, the abundance and the MSI stuff is kind of what we need first. Yeah, right. So the trend estimation informs our understanding of ecology. It informs our understanding of population status. But we need to try to do more than that. So, like from a mandate perspective. So that's my 2 cents.
And I'd agree, and I'd say if we're looking at those two things, that the MSI is probably more approachable than the NMIN at this point, because a lot of our existing methods to get at that are aerial surveys, are boat-based surveys, and the logistics of that, the feasibility of that has changed over time, and we can kind of see it when we look at the SARs in terms of how many of those NMIN estimates are now considered out of date. And so I think we can get more at the MSI through things like the happy whale, through things like public engagement with observations of scars and whatnot, and that there's a lot of value there. And then thinking about kind of what does it look like to come up with alternate ways to get at NMIN. And so I know NOAA's been using not dedicated marine mammal surveys, right, and taking advantage of that. As drone batteries become better, can we do aerial surveys using just drones for some species? Is it okay to use, as I said, with the kind of population dynamics models? Well, we knew what the abundance was in 2008. We have a model that would predict what it is now. Can we use that? I don't know what the letter of the law would be, but I think those are where we need to be thinking, kind of moving forward with these tools with regards to the SARs.
I would just add that I think the acute impacts are the thing that's the hardest, right? But also one of the more interesting. So, some disaster, an unusual mortality event, these are things we really care about and would like to get right, but you have to be in the right place at the right time to catch that. And so, to me, it seems like those are the places where the models and the data need to come together the most, and perhaps using hindcast methodologies is the one way that we're eventually going to be able to crack that nut, and I hope we do at some point.
Thank you. Maybe a follow-up for Kate. Lynn Thomas was at least one time very hardcore about using acoustics to make absolute abundance, right, which requires us to estimate call rate as a function of a bunch of variables. Do you feel that we've made a lot of progress tackling the question of call rate on Adonisetes, or are there so many variables that are becoming involved that it seems to be maybe not intractable, but something that requires more work than maybe we thought a couple decades ago?
I think we are pretty confident that we can do a decent job of estimating call rates and probability of vocalization, which are the two key pieces, and putting error bars on that. So, if you're good with error bars, I think we can get you there.
Okay, well, I feel like we've covered a lot of territory and kept you all awake. Well, I don't know if we kept you all awake, but kept you paying attention. I'd like to go and thank all our panelists, both remote and present, once again for a deep discussion on this topic. So thank you, everyone. And Peter, can I hand this back off to you?
Yeah, sure. We have 15 minutes more, but we're going to just cut it off pretty quickly. Again, thank you so much for an amazing day. All the panelists today have been fantastic. It's ambitious to put in an hour of discussion on any topic, and you guys have filled it incredibly. So thank you so much, and thanks to the morning panel. Just to say, tomorrow we're going to have a session tomorrow morning, regional updates, hot topics in the California current ecosystem. I'm sure we're not going to get every hot topic, but we are going to allow Karen Forney to give us her perspective on the last couple days and with relation to the more traditional assessment methods that we use. But she'll lead into Elliot Hazen talking about using climate-ready information in decision-making for multiple stakeholders. Ryan Bartling will talk about collaborative approaches to addressing whale entanglement, and Amy Lang will talk about monitoring the status of North Pacific gray whales. And then we'll bring it home with a talk by Clarissa Anderson asking, are we in a new era of marine mammal mortality events associated with harmful algal blooms in California? So it looks to be a really interesting session. We'll have some closing discussion and more chance, I think, for the public to weigh in. But we will finish, by the little bit after the end of the morning tomorrow. So again, thanks everybody. Have a good evening. We'll be around tomorrow morning.